We're now moving on to the last chapter that's in the textbook that we're going to cover, which is chapter 8. So it's this progression of moving on from chapters 4, where you're learning about polynomials, chapter 5, where you're learning specifically about quadratics and factoring and solving. And then it kind of flows into chapter 8, which is quadratic equations again, inequalities and functions. So the first thing we're going to do is 8.5. And I know this is weird because we're starting at the end of the chapter and then going back to the beginning. And it's because of a personal preference of mine. I like to see what it is that I am then going to be solving. So in section 8.5 and 8.6, it's all about graphing parabolas and learning about the features of parabolas. And then when we go back to 8.1, you're going to know the feature of the parabola that you are solving for. So our first objective in 8.5 is just to learn how to graph a quadratic function. So you've already done this using a table of values. We know that when the highest exponent is 2, we get this U shape, which is what is called a parabola. In this section, we're going to examine the graphs of parabolas, looking at a few specific details. Number 1 being the vertex. The vertex is the absolute minimum, or if your parabola is opening down, maximum on the graph. So this is your vertex. It's an ordered pair x, y. Same thing here. This is your vertex. It would be an ordered pair x, y. Then axis of symmetry. Every single parabola is symmetric about the vertex. So if I were to draw a line through the vertex, so if I was to go down here and this one down here, you can see that all the points are equidistant from this axis of symmetry. So every single point is symmetric across this line. In other words, I could fold this parabola over on itself and you'd get an exact match over this line. The axis of symmetry is always the line that runs through the vertex. So its equation is always the x value of the vertex. So if we said the vertex was AB, then the equation of the axis of symmetry would be x equals A. Direction of opening is another important thing. So whether it's opening up or down, and we'll discover when that happens. Then we're going to look at horizontal and vertical shifts. So we're going to be moving this graph up, down, left, and right. And then we're also going to be looking at stretching and compressing these graphs. So we're going to be looking at making them wider, making them narrower, and so on and so forth. But to do any of that, the first thing you need to know is what a basic quadratic function looks like. So a quadratic function is anything that can be written in the form f of x is equal to ax squared plus bx plus c. And you have to have real numbers for a, b, and c. Meaning they can't be imaginary, obviously, and the a can't be 0. And obviously the a can't be 0 because if a was 0, you wouldn't have your x squared term. So your most basic quadratic function is f of x is equal to x squared. We're going to rewrite that as y equals x squared. To figure out your basic shape, we're going to just use a table of values. So if I plug in x is -3, -3 squared is 9. If I plug in x is -2, -2 squared is 4. If I plug in -1, -1 squared is 1. If I plug in 0, 0 squared is 0. And then I'm going to get this symmetrical piece. It's going to turn around and I'm going to go back up. So I've got when 1 squared, I get 1. When x is 2 squared, I get y is 4. When x is 3 squared, I get y is 9. So if I went to go graph this, you can see that I'm getting these symmetrical points. So I've got this point at -3, 9. Well, I also have a point over here at 3, 9. I have a point at -2, 4. I also have a point over here at 2, 4. I have a point at -1, 1. I have a point at 1, 1. And then I have this point at 0, 0. So this is my basic parabola. I'm going to connect my dots with a U shape as best I can. It's not a V, it's a U, so make sure it's rounded at the vertex. And it goes on and on forever. So like I was mentioning, the vertex is your point that your graph turns around. In a basic parabola, your vertex is 0, 0. Your axis of symmetry is the line that goes through the x value of the vertex. So it's this vertical line. It's always vertical for a parabola. And it's going to go through x equals 0. The axis of symmetry is always an equation because it's an axis, it's a line. And so you have to put x equals 0. If you just put 0, you won't get it right because it's like, well, what's 0? Y, x, it matters. The domain of your basic parabola is always all real numbers. So you are more than welcome to put XER or negative infinity to infinity. And that's because there's nothing you can't put in for x. There's no x's in denominators because that would be a rational equation. There's no x's underneath the radical sign because that would be a radical equation. So for a quadratic, you just have an x squared, and so you can put anything you want in for x. The domain, however, because it's a y equals x squared graph, you're never going to get this negative y value because you're always squaring the x. So for your basic parabola, your range is going to be y is greater than or equal to 0, or you can put square bracket 0 up into infinity. So this is your basic information. This is the stuff that you should know off by heart. And then what we're going to do is just transform this base graph. So objective 3. Objective 3, we're going to look at the coefficient on x squared to predict the shape and direction in which a parabola opens. So I'm going to make this even smaller so I can fit it all on one page. So what I'm going to look at is when y equals x squared, when y is equal to negative x squared, when y is equal to 2x squared, and so on. So let's do it using a table of values. So we already know y is equal to x squared. So this is just putting in negative 2 squared, I get 4. Negative 1 squared, I get 1. 0 squared, I get 0. 1 squared, I get 1. And 2 squared, I get 4. So it's that basic shape. This is my vertex here at 0, 0. And then you always go over 1 and up its square, over 2 and up its square. In fact, I could do more points. I could go over 3 and up 9. And then I'm going to have the symmetry on the other side. I'm going over 1 and up 1, over 2 from the vertex and up 4, over 3 from the vertex and up 9, or I can literally just draw the points across. So this is my basic parabola. This is y is equal to x squared. And now what we're going to do is compare every other graph to this. So I'm going to switch colors. And I'm going to do y is equal to negative x squared. The only difference is that after you square the x, you're going to times it by negative 1. So if I do y is equal to negative 2 squared, which is 4, I'm going to then multiply it by negative 1. So this is going to become negative 4. This one's going to become negative 1. This is 0, negative 1, negative 4. So this second parabola is going to have that same vertex, but instead of going over 1 and up 1, I'm going to go over 1 and down 1. Instead of going over 1 and up 1, I'm going to go over 1 and down 1. Instead of going over 2 and up 4, I'm going to go down 4, over 2 and down 4, over 3 and down 9. So I get the same parabolic shape. It's just that instead of opening up, it's going to open down. So y equals negative x squared. The only difference is that it opens down. We call this a reflection in the x-axis, but that's not so important for math. So I can't write and talk at the same time. Math 50, reflection in x-axis. But if you are going on to Math 60, this might be something that's important to know, that we're reflecting the y values over the x-axis. So this is considered a reflection in the x-axis. But for us, for Math 50 point of view, as long as you know that when it's negative, it opens down, that's important. Let's move on to the next one. Let's pick pink or magenta or whatever this is. So now the only difference is that after I square the x, now I'm going to be timesing that squared x value by 2. So when x is negative 2, I get x squared is 4. Then I'm going to times that by 2 and get 8. So this one would be 2, 0, 2, and 8. So what I've done is I've taken all of these x squared values and times them by 2. So the x value is not changing. What's changing is what's happening to the x. So I'm squaring it and then timesing by 2. So I'm going to get the graph. It's going to start at the 0, 0. Instead of going over 1, up 1, I'm going to go over 1 and stretch that by 2, which that's a bad. If I could just like make that look nicer. It matters. It's really hard to be perfect on these graphs. So this one was over 1 and up 1, and then through that 4. And then my next graph, it's going to go over 1 instead of up 1. It's going to stretch by 2. Instead of going over 2 and up 4, it's going to stretch by 2 and go up to 8. And then I'm going to do symmetry on the other side, over 1, up 2, over 2, up 8. So that I get this same parabolic shape, but it's narrower. It's been stretched vertically by a factor of 2. So y equals 2x squared. How does it compare to y equals x squared? Well, I can simply say it's narrower. So again, what I'm writing first is your Math 50 terms. If you are going on to Math 60, maybe you'd want to look at the fact that this is stretched vertically by 2. All the y values were stretched by 2. Next one, -3. Okay, so this time after I square the x value, so again, same x values, the only thing that's changing is y, is that after I square and get 4, now I'm going to times that 4 by -3, so I'm going to get -12. And then here, instead of going -1, 1, I'm going to stretch that by -3, and it's going to go -3. 0 times 0 is still 0, or 0 times -3 is still 0. 1 is going to -3, -12. That's symmetry point of view. So if I was graphing this without the table of values, I'd have my vertex at 0, 0. Instead of going over 1, down 1, I'm going to stretch that by 3. So I'm going to go over 1 and down 3. I'm going to do that on the other side, over 1 and down 3. And then I would go over 2, and instead of going down 4, I would stretch that to 12, except that it's not going to fit. So I'm just going to make this a very narrow graph. Okay, same thing on the other side. Awesome. Okay, let's move on to the next graph. There's color. Okay, so now we're going to do y is equal to 1/2 x squared. So now what I want, oh, sorry, I didn't finish that one off. Right. So if we're talking about y equals -3x squared, I want you to notice that it opens down. And that's because of that negative value that's making all the y values negative. And then it's also narrower. If I was talking in terms of Math 60 words, I would say that it is reflected in the x-axis and it is stretched vertically by a factor of 3. But again, that's kind of getting used to the language. In Math 50, they definitely just say narrower or opens down. But if you want that, you don't have to write this. Reflection in x-axis and vertical stretch by 3. Okay, moving on to the next one. Okay, we are going to look at y is equal to 1/2 x squared. So I want you to start asking yourself, is this graph going to open up or is it going to open down? So we're talking about y equals 1/2 x squared. Because the 1/2 is positive, it's not going to be reflected in the x-axis, so it's going to still open up. What's the difference? Well, the difference is that after I square the x values, I'm going to times them by 1/2. And so instead of getting this point at 4, I'm actually going to get a point at 2. Instead of getting a point at 1, I'm going to get a point at 1/2, still get 0, still get 1/2, still get 2. So what does that mean for my graph? Well, if I go to graph it, I've got 0, 0. Instead of going over 1 and up 1, I'm going to go half as high. Instead of going over 2 and up 4, I'm going to go half as high. Instead of going over 3 and up 9, I'm going to go half as high to 4.5. I could take another point. Usually I would go over 4 and up its square to 16, but I'm going to go half as high to 8. So I can fit more grid points on because this graph has been compressed. So it's going to be symmetric on the other side. So if over 1 and up 1, I go over 1 up 1/2, over 2 and up half as high to 2, over 3 and up to 4.5, over 4 and up to 8. And this is my y equals 1/2 x squared graph. So we would say that this graph is wider. Okay, when it was stretched, so when the a value was greater than 1, it became narrower, it got taller. And when the a value is less than 1, it gets compressed. And so you end up with this wider graph. We would still call this, some people say it a vertical stretch by 1/2. Some people say it's compressed by 1/2. The wording kind of changes. But the important thing is that it affected y and that it got wider. So it's a vertical stretch by 1/2 or a compression by 1/2, whatever you want to call it. Last graph, when we're looking at this one here, let's pick orange. When we're picking this one here, we've got y equals -1/2 x squared. So how is that going to compare to this graph? What's going to be the biggest difference between y equals 1/2 x squared and y equals -1/2 x squared? It's still going to be wider, but it's going to open down. So I'm going to start at that vertex of 0, 0, and then instead of going 1/2, I'm going to go -1/2. negative 2, negative a half, negative 2. So now I don't do these tables of values every single time I graph one of these. What I do is I start with my vertex at 0, 0. Normally I go over 1 and up 1. Because it's negative, I'm going to go down. And because it is multiplied by a half, I'm only going to go half as high. Normally I'd go over 2 and down 4. I'm only going to go down 2. Normally I'd go over 3 and down 9. I'm going to go down 4.5. Normally I'd go over 4 and down 16. I'm going to go down 8. And then you can just do that symmetry on the other side. You don't even have to count. You can just go across and make sure that it is symmetrical. And then you join your points, and we get that graph that is wider and opening down. Okay, so that's your introduction to the A value. There's a little summary at the bottom of this page. It says, does changing the value of A affect whether the parabola opens up or down? Yes. How so? If the A value is positive, it opens up. If the A value is negative, it opens down. Does the value of A affect the location of the vertex? Did the location of the vertex ever change? No. It was 0, 0 every single time. Did the value of A change the axis of symmetry? Well, the axis of symmetry goes through the x value of the vertex. So if the vertex didn't change, then the axis of symmetry won't change. The axis of symmetry is x equals 0. So the answer is no, it's always x equals 0. So the vertex is always 0, 0, and the axis of symmetry is always x equals 0. All right, so we're going to take a pause here, see if you can find some questions in the homework that only put in an A value. So the only thing they can look like is y equals a x squared.